Principles of Operating Systems. Chapter 4, Concurrent Processes, Synchronization, Deadlocks, Starvation. All the modern operating systems have to deal with concurrent processes. Processes that have processes executing simultaneously. Even the simplest single-user personal computers have several things going on at once. They're controlling the display on the monitors. They are watching for the user to input from the keyboard or the mouse, and also executing application programs. In fact, most modern computing systems have more than one processor. Most modern computing systems are multi-processor systems. And although the older single processor systems can give you the impression that there is concurrent processing, they use time slicing to permit several processes to share access to the processor. Process one, execute one for a while, another for a while, another for a while. But multiprocessor systems really do have different processors executing different processes at the same time. Now, whenever we have multiple processes active at the same time, it's quite normal, expected. Some of them will have to interact. One process might provide information that another one needs. One process might simply need to determine what the state of another process is, but they might have to interact. Interaction and synchronization of concurrent processes usually does, end up being very complex and leads to very subtle problems. Concurrency also gives us the possibility of deadlock situations and/or starvation, as was mentioned back in Chapter 2. Concurrent processes typically communicate with each other by leaving data, messages, information in commonly accessible memory locations. One process puts data in the buffer where the other process can access it and make use of it. Now, when you have concurrent processes accessing common locations in memory, there are lots of things that can go wrong. This is a very complex and subtle issue, and the errors can be very difficult to detect and eliminate. But synchronization is essential for concurrency to work at all. As a relatively simple example of the kinds of synchronization problems that we can get when we have mutual access to the same buffer, consider two processes, producer and consumer, with a shared buffer, buff. Producer creates values and stores them in buff for consumer to read and do something with. An example might be consumer is a printer driver and producer a word processor, storing text characters in buff, and consumer reading the characters from buff and sending them to a printer. Consumer, of course, should not try to read a value out of buff until there's actually something there to read. Producer should not try to store something new in buff until after a consumer has used anything that was stored there before. And we're going to assume that there's only one instance from each procedure. Now we could try to set this system up using two procedures. Producer with a parameter. If the buffer is null, pause. When it continues, set the contents of the buffer to be the value of the parameter. Then initiate consumer and end procedure. Consumer does whatever it is that it does with the contents of the buffer, sets the contents of the buffer to null, and checks whether producer has been paused. If it is paused, resume it and terminate. Looks like it ought to work, but there's a problem. Now we're assuming, of course, we're working in a multi-programming system, and these two processes can run concurrently, either in time slices or in separate processors. Now, the following situation might come about. Producer stores a value in the buffer and initiates the consumer and terminates. Producer then, before consumer gets a chance to continue or to do much, producer restarts with a new parameter value. Now, consumer has not changed, has not set the buffer to null, so buffer not equal to null. This condition in producer gets evaluated, and it's true. Before going on and executing pause procedure, consumer takes over, sets the buffer to null, does whatever it does with the contents, sets the buffer to null, and since producer has not executed pause procedure is not true, so consumer does not resume procedure, does not resume producer, but goes on and terminates. Now producer takes over again. It left off after evaluating buffer not equal to null, getting true. So since the condition was true, it pauses. And at this point, the system is deadlocked because producer's paused, consumer is not executing. The only way consumer can start is if producer starts it. But producer cannot start it because it's paused, and the only thing that can resume producer is consumer, which is not executing. Here we have the situation. It starts off with producer and consumer are both inactive and the buffer is null. And producer starts executing with parameter v1. Producer is now active, consumer is still inactive, and the buffer is still null. Producer checks whether buffer is null. Not. It's not null, so the condition is false. Producer is still active. Consumer is inactive. Buffer is null. And producer continues. Sets buffer to be V1. Producer still active. Consumer inactive. Buffer is now V1. Now, producer initiates consumer. So producer is still active. Consumer is now active. Buffer is still V1. And producer goes on to terminate. So producer is now inactive. Consumer is active. The buffer is V1. And producer starts executing. Again, producer now active. Consumer is still active. Buffer is V1. Producer checks whether buffer is null. Not null. So the condition is true. Producer is active. Consumer is active. Buffer is still V1. But at this point, consumer starts executing, and it does whatever it does with the contents of the buffer. Producer still active. Consumer still active. Buffer is still V1. Consumer goes on, resets the contents of buffer to null. Producer active. Consumer active. Buffer is null. Consumer checks whether producer is paused. Producer has not paused itself yet. Producer is still active. Consumer still active. Buffer is null. Okay. So consumer, since producer is not paused, consumer goes on to terminate. So producer is still active. Consumer inactive. Buffer is null. Producer now continues, having checked whether the contents of buffer were null, got true, and it pauses. So now producer is paused, consumer is inactive, buffer contents are null, and everything is deadlocked. The previous example is typical of the problems that occur in synchronization situations. One way to avoid this kind of a problem is to ensure that certain kinds of processes, once initiated, must be allowed to complete before others can be allowed to continue. The example in the previous example is if buffer is not null, pause procedure. The problem occurred when the if evaluation was stopped and the consumer began executing before the consequence pause procedure executed. A common element of successful synchronization schemes is that of a critical region whose execution must be handled as a unit that cannot allow other processes to execute while it is active. There have been several mechanisms developed that support implementation of critical regions. The most commonly used ones are the test and set and semaphores. test and set was first introduced by IBM for the 360 and 370 computers. It's a single instruction, has the effect of identifying, reading the contents of a memory location, and then writing a 1 into that memory location, all as a single non-interruptible operation. If multiple processes access the same memory location, then when a process is executing the test and set, no other process can start a test and set, can start any other operation involving the location until the first test and set is finished. Non-interruptible. A semaphore is a non-negative integer variable together with two operators, P and V, to test and decrement the value in the variable or to increment the variable. The three things together form an abstract data type that's widely used for controlling access for resources used by multiple processes. The letters P and V come from Dutch, test and increment. The concept was designed by Edgar Dijkstra, obviously Dutch. There are two kinds of semaphores: counting semaphores and binary semaphores. In a binary semaphore, the variable S can only have values 1 or 0. Binary semaphores are utilized primarily for mutually exclusive critical regions, mutually exclusive mutexes. For binary semaphores, when a process attempts to execute P of S, if S is 1, then it sets S to 0 and the process proceeds. Now, checking for whether it's 1 or 0 and setting to 0, the combination is atomic, so that nothing interferes between testing and setting to 1, setting to 0. If the value is 0, then the process is stopped. It's not allowed to proceed. It'll have to execute P again in order to eventually proceed. It might just be returned to the ready queue, or the semaphore S might have its own queue of blocked processes. If S is binary and a process executes V of S, then S gets set to 1. If there is an associated queue of blocked processes and it's not empty, then one of the processes gets moved from blocked to ready, to the system ready queue, so that when its turn comes to start executing, it can try to execute P once again. A counting semaphore, the variable s can be 0, 1, 2, 3, any non-negative integer value. Counting semaphores generally get used for keeping track of how many units of some type of resource are available. If S is a counting semaphore, then executing P of S will, if the value is 0, then it acts just like it was a binary semaphore. The process is stopped, not allowed to proceed, and has to try again to proceed. The process might just be returned to the ready queue to wait another turn, or it might be placed in a blocked queue for the semaphore S. If, on the other hand, the S is greater than 0, then executing P of S results in decrementing the value in S and permitting the process to continue on. Notice that P is atomic, so in between checking the value of S and decrementing the value in S, nothing can be come in between those two actions. If S is a counting semaphore, then V of S results in incrementing the value in S, and if there is a non-empty blocked queue for S, then all of the processes in that queue will get transferred into the ready queue for the system so that each in turn can attempt to execute P. We can describe the P and V semaphore operators using the terms wait and signal. Wait, meaning if the value of the semaphore variable is positive, decrement it and go on executing the process. If the semaphore variable is 0, then block the process until the semaphore value has become positive. Signal, increment the value of the semaphore if it's a counting semaphore, or just set it to 1 if it's binary. If there are any blocked processes, then allow one of them to attempt to proceed, to check, execute the P again, and continue.